So, VSEPR theory, predicting molecular geometries. These are the instructions the book gives you. Draw the Lewis structure. Find the total number of electron groups on the central atom. Find the number of bonding groups and the number of lone pairs. Well, and I should have edited this because it's not chapter 11. And then they say, refer to table 11.1 to determine the electron geometry and molecular geometry. No. Because I'm not going to give you that on an exam. I should have zoomed out further. Think about how balloons would arrange themselves, and then imagine that the lone pairs are invisible balloons. Describe the shape. Okay? That's what you do. Then you could use the table to check yourself. Okay, predict the molecular geometry and bond angle of ClNO. Now, they're not specifically telling us what's the central atom. Oftentimes, the order that they're presented in is for a reason, right? And so we're going to put nitrogen in the middle and oxygen on one side and chlorine on the other side. And actually, turns out it doesn't matter for this one. We'll get the same geometry.
And for the central atom, does it matter depending on the number of bonds that one can form?
Well, it will. I mean, you can't get an octahedral shape with carbon as the central atom because it can't expand its octet. Yeah.
Oh.
Right. So let's just put these in a line: Cl, N, and O, and then this is a little review for the exam, right? Writing Lewis structures. Chlorine has 7 valence electrons. Nitrogen has 5. Oxygen has 6. 7 and 5 is 12, and 6 is 18 valence electrons. I've got 2, 4 already for bonds. 6, 8, 10, 12, 14, 16, 18. So is this good? No. I don't have an octet on the nitrogen. And if I do formal charges, I'll find out that I don't have 0 formal charges here, and nitrogen isn't one that will put up with an incomplete octet anyway. So we need to do some more sharing. It's not going to matter for the geometry, but for a correct Lewis structure, it would actually matter. We have to put a double bond in here. Should I give the double bond to chlorine or to oxygen? To oxygen. Because oxygen likes to have 2 bonds, right? When it has 2 bonds, then it's got a 0 formal charge. So we'll do that. And then if we evaluate formal charges, we'll find that they're all 0. Because here's nitrogen with an octet and 3 bonds, chlorine with an octet and 1 bond. Everybody's really good here. So that's the Lewis structure. Now we can predict molecular geometry and bond angle. They're having fun in lab. I'm sure that they make fun of us sometimes too. So we're going to look at the central atom, and we're going to ask ourselves, well, how many electron groups around the central atom? I'm hearing 2, 3, and 4. It's 3. Single bond is 1 group. Lone pair is 1 group. Double bond is 1 group. It's not pairs, it's groups. So 3 groups, what do 3 groups do? They make a triangle that's flat, right? Trigonal planar. So that's relatively easy to draw, right? Flat triangle. But there are lone pairs. So our electron geometry, I'm just going to call this EG. Electron geometry is trigonal planar because we had 3 electron groups. But what's the molecular geometry? It's bent because one of these is a lone pair. Well, let's make it this one. It's a lone pair. Okay, so the molecular geometry is bent. Ooh, that was big. It's not bent, it's just bent. Okay, so there's our molecular geometry, and it wants the bond angle. So in an ideal trigonal planar, this would be what? 120. But we've got a lone pair. So is this angle going to be more than 120 or less? It's going to be less than 120. Because this is more repulsive, and so even though these two bonds don't want to get closer together, this is worse. And I am going to squeeze, you're the lesser of these two evils. I'll squeeze a little closer to you, right? So the answers to this question would be bent and less than 120. Now, if it was multiple choice, it might not say less than 120. It might say 107 and 90 and 120 and 180. And so then you'd pick the one that's just a little bit this less. I didn't mean to say 107. I meant 117. Any questions? Predict the molecular geometry of I3 minus. Anybody recognize this ion from the worksheet? So we're going to have to do the Lewis structure for this, and so that's going to give you the answer to the one on the worksheet, so pay attention, right? Well, I3 minus. The I's are going to have to be in a line, because we can't make a triangle with them. And we've got 3 iodines. They each have 7 valence electrons, plus 1 for that extra charge, so 22 electrons. I have 2, 4. So I'm going to start at 6. Whoops, that's too close. 6, 8, 10, 12, 14, 16, 18, 20, 22. Can I put them on the central iodine? Is iodine big enough to handle it? Yeah. So I'm going to put them in here. And so you're like, well, you know, I'm kind of having a hard time with all those dots so close together. So you might want to just spread them out a little bit and say, well, I'm going to do this and this so I can just see it a little better. And then it's an ion, so we're going to have to put a charge on it. If we look at formal charges, we will see that this iodine is 0 and this one is 0 and the one in the middle is -1. Somebody has to be -1, and so this is the best Lewis structure. Now we can predict the molecular geometry. How many electron groups around the central atom? 5. So we have 5 electron groups. So our electron geometry is, what do 5 balloons do? Trigonal pyramid. Pyramid, just squeeze it in there. So you can kind of imagine that's 3-dimensional. Shouldn't be too hard. So that's our trigonal pyramid. We have 3 lone pairs. Where do we put them? Along the equatorial, because that's where they're going to have more space. So if this is the little girl's head and her body and her feet, this is her tutu, and we're just going to make parts of her tutu invisible. She still has a leotard on underneath, so it's all very decent and everything. I know. I don't want to be accused of anything. So that's where the lone pairs are. So it's linear. Yeah. So the molecular geometry is linear. That's the answer to the question. That's doable, huh? Fairly straightforward. It's going to take some practice. We're going to practice. We got the worksheet coming up that we're going to practice on this. You can maybe see how the Lewis structure worksheet is going to lead into predicting molecular geometries, because worksheet 11 is going to use the same molecules and polyatomic ions. So you will already have written the Lewis structures for them and taken a look at how many groups are on the central atoms, right? It doesn't, that part doesn't match up exactly, but I have to work on that. Bless you. So how do we represent these on paper? So this is a table or illustration from your book, which is kind of helpful. When we draw just a straight line, we intend that to mean that it's in the plane of the screen or the paper. This solid wedge is like jumping out at you, like three-dimensional, right? It's coming out at you. And this dashed wedge is behind the screen. It's a dashed line because if the screen is solid, you can't see it back there, but it's back there. So some of the structures are easy to draw: linear, trigonal planar, bent, because those fit in the plane. If it's a planar structure, just make it flat in the plane of the screen. Don't try to make it more difficult. Then tetrahedral. So here we can draw 3 of them in the plane, and then there's one coming out at you and one going behind. And then they've got the little model showing you that. Trigonal pyramid is very similar, just missing the top here. Here's a trigonal bipyramid. So these 3 are in the plane, and then one behind and one out. And the seesaw and the octahedral. Square planar's flat, so it's easy. So you should practice doing this. What's most important at this point is that when I draw it like this, you know what I'm trying to tell you. We do a lot of this in OChem because we need to represent there the three-dimensional shape of the molecule can be extremely important. Well, what if we have more than a central atom with stuff around it? A larger molecule with more than one interior atom. What do we do then? Well, you look at each of the interior atoms separately and identify its geometry. So an example here is the amino acid glycine. So here we have, there's actually 4 interior atoms. And we've got the Lewis structure here. And so if we look at this nitrogen, we see that it has 4 electron groups. So that's tetrahedral electron geometry, and 1 lone pair, right? So that's going to give us a trigonal pyramid shape. And then over here, they've tried to show that's trigonal pyramid. This is kind of sticking out. Here's this carbon. This carbon has 4 electron groups, tetrahedral, no lone pairs. So the molecular geometry is also tetrahedral. This carbon has 3 groups, trigonal planar. No lone pairs, so still trigonal planar. Here we've got 4 electron groups and 2 lone pairs. So tetrahedral, make 2 of them invisible, it's bent. And then we can try to draw it. So they've got an illustration of the model. And we're going to do this one. So this is acetic acid. Predict the geometry around each interior atom in acetic acid and make a sketch of the molecule. I won't make you do that on an exam because I don't want to have to evaluate it. Just, being honest there. Well, we need a little more detail, and instead of redrawing the whole thing, I'm just going to expand on this a little bit. So this has 3 hydrogens attached to it. And this has a hydrogen attached to it. Just spreading it out a little bit so I can do the Lewis structure right on top of it. So if we count up electrons, Let's see, we have 4 hydrogens, each with 1 valence electron. We have 2 carbons, each with 4 valence electrons, and 2 oxygens, they each have 6. So 12 and 8 is 24. So we count the bonds first, and we're kind of cheating because they already told us there's a double bond here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Just filling in the octets. Oxygen was the only one that didn't have an octet. So that's the Lewis structure. So this carbon, how many electron groups? 4 electron groups. Are any of those lone pairs? No. So the molecular shape and the electron geometry are the same of it all. What's the shape? Tetrahedral. And this carbon, how many electron groups? 3. 3 electron groups. Any lone pairs on that carbon? No. What shape? Yeah.
Why are there not lone pairs? Because if you separate them.
Well, so this carbon has a double bond and a single bond and a single bond, and there aren't any dots on it. So there aren't any lone pairs on this carbon. And there aren't any lone pairs on this carbon.
So
But the oxygen has lone pairs.
the carbon is like when we split them up to each molecule, I guess it could take the 2 electrons.
Well, we're not taking the molecule apart. If we were taking it apart, then yeah, something would have to happen with those. But we're keeping it together. We're just looking at each of the inside atoms separately. Okay. So 3 electron groups is trigonal planar. And then this oxygen, I'll maybe make that one blue. So the oxygen on the end there. How many electron groups? 4 groups. 4 electron groups. Any lone pairs? Yeah. 2 lone pairs. Call those LP. 2 lone pairs. So the electron geometry would be, for 4 groups, tetrahedral. And then 2 of those balloons are invisible. What's the name of what's left? Bent. So this is bent. So that's predicting the geometry around each interior atom. And then it says sketch it. Nice, right? So sketching something like this, you want to put as many things as possible in the plane of the paper. Minimize the stuff that's sticking out and behind. So I'm going to start with that carbon in the middle. So that's the carbon in the middle, and that's trigonal planar. So this is the oxygen, and there's a double bond here. And then I'm going to have a bond over here and a bond over here. And this is going to be oxygen, and this is going to be the other carbon. And I'm going to do the oxygen next because that's easier. That's bent, right? So I could bend up or bend down. I'm going to bend up, and there's the hydrogen. So this angle here, a little less than 109.5. This angle, a little less than 120. But it's not really asking us that. Then this carbon is tetrahedral. So I've got one here. I can draw another one kind of down here that's in the plane. And then I'm going to have one that's sticking out That's coming out to get you. And then this one is behind. And as ugly as that is, it's actually a pretty good drawing. Any questions? What's the molecular geometry about nitrogen in CH3NH2? Well, they call this a conceptual question, but actually we have to draw a Lewis structure here. The 3 hydrogens listed after the carbon and the 2 hydrogens listed after the nitrogen tell me that 3 of the hydrogens go on the carbon and 2 go on the nitrogen. If we count up electrons, we'll find that we only have 2 more to put on, and they're going to be a lone pair on nitrogen. So that's just kind of speeding up the process. What's the molecular geometry around the nitrogen? Do the electron geometry first.
Yeah, that's
Tetrahedral. 1 lone pair. Trigonal pyramid. Because what we have there we had our tetrahedron, right? And we're going to make 2 of them invisible. I'm going to make these guys invisible. No, not 2. Sorry, I lied. 1. I'm going to make 1 invisible. It's more convenient in order to see the shape to make that one invisible. And what I've got left is weird. That's a trigonal pyramid. Questions?